Something astonishing is unfolding in our understanding of the early universe. What has the James Webb Space Telescope captured at the very edge of time? And why are some researchers asserting that these groundbreaking discoveries could revolutionize everything we believe about the cosmos? For many decades, our narrative of the universe has been encapsulated in the Lambda CDM model, a comprehensive framework that explains our cosmic history from the moment of the Big Bang, around 13.8 billion years ago, to the expansive universe we explore today. This grand tale is supported by a wealth of evidence and has guided cosmological thought for over 50 years. However, recent data from the James Webb Space Telescope is sending shockwaves through the scientific community, revealing phenomena that our existing models suggest should not exist so early in the universe's timeline. These revelations are not trivial. They have led some scientists to declare a crisis in cosmology. This emerging dilemma calls into question our fundamental comprehension of the universe itself, raising the possibility that our current model may be incomplete or even fundamentally flawed. The work of Nobel Prize-winning scientists is central to this escalating crisis. To grasp the magnitude of this revelation, we must first delve into the very narrative being disrupted, the Lambda CDM model, our cosmological standard. The story begins 13.8 billion years ago with the Big Bang, a moment not merely marked by a violent explosion in space, but as the genesis of space and time itself. From an infinitely dense point, the universe began to expand, creating the intricate fabric of reality. In those initial moments, the universe swelled exponentially, an event known as cosmic inflation. As this vast expanse continued to unfold, it began to cool, allowing basic particles to coalesce into hydrogen and helium atoms. This transformative process released a brilliant flash of light, an echo of which we still observe today as the cosmic microwave background. This CMB serves as a snapshot of the infant universe, one of the most compelling pieces of evidence supporting the Big Bang theory. Following this initial phase, the standard model posits a gradual evolution as gravity acted upon minute density variations within the young universe. Over hundreds of millions of years, gravity drew gas together into increasingly denser clumps, leading to the birth of the first stars. These primordial stars, though fleeting, ended their life cycles in spectacular explosions, forging heavier elements like carbon and oxygen essential for life. From the remnants of these luminous giants, new stars emerged, gathering over billions of years into the first galaxies. The model foretold that these nascent galaxies would be small, irregular, and chemically simplistic, akin to cosmic infants, embodying the early stages of cosmic evolution. This timeline stood unchallenged for half a century, until the James Webb Space Telescope opened its gaze upon the universe. The James Webb Space Telescope, the most sophisticated observatory ever constructed, boasts extraordinary capabilities. Its primary strength lies not only in its size, but also in its ability to peer into the cosmos using infrared light. This capability is crucial for two significant reasons. First, as the universe expands, the light emitted by distant celestial objects is stretched into the infrared spectrum, a phenomenon known as redshift. Designed specifically to detect this redshifted light, Webb can observe the earliest structures in the universe. Second, infrared light possesses the unique ability to penetrate cosmic dust clouds that obscure the formation of stars and galaxies. In essence, the JWST serves as a time machine. When it gazes at a galaxy located 13.5 billion light-years away, it is not merely observing it as it exists now, but rather glimpsing its state 13.5 billion years ago, when the universe was a mere few hundred million years old. The observatory was engineered to witness the birth of the first stars and galaxies and corroborate our standard narrative about the universe's evolution. Although scientists anticipated surprises, the findings from Webb's initial observations were beyond anything they could have prepared for. These revelations didn't merely add new layers to our understanding, they began to challenge the very bedrock of our cosmological foundations. When astronomers analyzed the first data from the James Webb Space Telescope, they encountered a perplexing problem. They had anticipated uncovering small, nascent galaxies, often referred to as infant galaxies, from the early universe. Instead, what was revealed were galaxies that exhibited characteristics more akin to teenagers or even young adults. For instance, JWST detected the presence of galaxies that existed merely 280 million years after the Big Bang, a time frame that is remarkably short in the grand scale of cosmic history. Prior to these groundbreaking observations, the prevailing belief was that the earliest galaxies began to form around 500 to 600 million years following the Big Bang. To understand the significance of this finding, we need to consider the implications for how galaxies develop. The standard model of cosmology posits a gradual evolution as gravity acted upon minute density variations within the young universe. Over hundreds of millions of years, gravity drew gas together into increasingly denser clumps, leading to the birth of the first stars. These primordial stars, though fleeting, ended their life cycles in spectacular explosions, forging heavier elements like carbon and oxygen essential for life. From the remnants of these luminous giants, new stars emerged, gathering over billions of years into the first galaxies.
The surprise came when JWST discovered that well-structured, massive galaxies seemed to have formed in significantly less than this predicted timespan. Imagine discovering a fully grown oak tree in a location where you expected to find only a tiny sapling. That's how astonishing this revelation was. The scientists responsible for these observations meticulously re-examined their data, presuming it might contain errors. However, the data consistently affirmed their initial findings. This stark contradiction compels us to reconsider our timeline of cosmic evolution. It raises critical questions. Did the universe mature at an astonishingly faster rate than previously believed? Or does the physics governing the early universe operate under principles distinct from those described by our current models? This discovery of early, seemingly impossible galaxies ties into a broader and significant issue that many in the scientific community refer to as the crisis in cosmology. At the heart of this crisis lies what is called the Hubble tension, which revolves around a fundamental question: what is the current rate of expansion of the universe? Nobel laureates such as Adam Rees have been instrumental in exploring this issue. There are two primary methodologies used to ascertain the Hubble constant, which quantifies the universe's expansion rate. The first approach involves examining the early universe by utilizing data extracted from the cosmic microwave background, the remnant radiation from the Big Bang. This data is integrated into the standard model of cosmology, which then estimates how fast the universe should currently be expanding. This method yields a Hubble constant value of approximately 67 kilometers per second per megaparsec. The second method focuses on the local universe. In this approach, astronomers, including Rees's team, directly measure the distances to proximate galaxies and observe how rapidly they are receding from us. They employ standard candles, such as specific types of stars and supernovae whose intrinsic luminosity is well established. In contrast, this method provides a higher Hubble constant value of around 73 kilometers per second per megaparsec. For years, many researchers hoped that advancements in measurement techniques would ultimately reconcile this discrepancy. JWST was particularly anticipated to offer definitive answers, serving as a possible tiebreaker. Instead, it not only confirmed the precision of both methods, but also underscored the real existence of this discrepancy. The universe seems to be expanding at two different rates, prompting deep concerns for cosmologists. This situation presents a considerable crisis for the field. It implies that our current standard model, a framework that successfully connects the early universe with the present cosmic landscape, might be fundamentally inadequate. If the universe operates under a set of principles that diverges from our established scientific understanding, we may find ourselves grappling with a reality that resembles another universe entirely. In the face of such a serious theoretical crisis, scientists often seek radical new concepts. One intriguing idea is that novel physics might have influenced the dynamics of the early universe. For instance, the notion of early dark energy suggests there was a temporary energy field that could have propelled the universe into a period of accelerated expansion shortly after the Big Bang, potentially providing a resolution to the Hubble tension. Another, more revolutionary proposal suggests the necessity of modifying Einstein's theory of gravity when applied across cosmic scales. If gravity had manifested differently in the early universe, possibly exhibiting a stronger force, it might explain how these sizable galaxies formed rapidly, defying long-held expectations. Such shifts in understanding could rewrite our cosmic narrative and lead to profound changes in our comprehension of the universe. But perhaps the most intriguing evidence emerges from a recent study of early galaxies observed by the James Webb Space Telescope. Modern cosmology is fundamentally based on the assumption of isotropy, which means that the universe appears uniform and the same in all directions. According to this principle, one would expect galaxies to exhibit random rotational directions, resulting in approximately 50% of them spinning clockwise and 50% counterclockwise. However, this particular study has revealed a surprising trend. A significant majority of early spiral galaxies seem to be spinning in a consistent direction. This finding raises profound questions about the nature of our universe. It suggests the possibility that the universe itself may not be perfectly isotropic, and that it could have originated with an overall angular momentum or spin. Such a revelation poses a significant challenge to our existing standard model of cosmology, which does not account for this phenomenon. This intriguing outcome has rekindled interest in a speculative framework known as black hole cosmology. This theory posits that our universe may exist within a massive black hole that originated from a larger parent universe. If this is the case, it could potentially explain the observed cosmic spin, as our universe would inherit the rotational characteristics of the black hole from which it was formed. This interpretation offers a literal perspective on the notion of another universe, suggesting that we might reside within an entity that is part of a broader cosmic tapestry.
So, where do we find ourselves today? We stand at the precipice of what could be a groundbreaking scientific revolution. The James Webb Space Telescope was designed with the purpose of enhancing our understanding and mapping of the universe. Instead, its groundbreaking observations indicate that our current map lacks crucial features and complexities. The so-called impossible galaxies, the discrepancies known as the Hubble tension, and the unexpected evidence pointing to a spinning cosmos collectively suggest a fundamental flaw in our standard model of cosmology. Acknowledging our lack of understanding is not a sign of failure. Rather, it marks the beginning of a new exploratory venture. The once simple narrative of a slowly evolving universe is gradually being supplanted by one that is far more intricate and enigmatic. This opens a door to the potential discovery of new forces, particles, or even alternative physical laws. It leads us to ponder whether we are just beginning to uncover the true essence of our cosmic environment. The astonishing observations made by JWST are not just sightings of distant objects, they are clues that reveal the universe is far more bizarre and complex than our most advanced theories have led us to believe. We are not nearing the conclusion of physics. Rather, we stand at the dawn of a new era in our understanding of the cosmos. Well, that's all for today. I hope you enjoyed this exploration of ongoing developments in cosmology. What do you think is happening? Are we simply missing a few critical pieces from our standard model, or are we on the verge of uncovering an entirely new framework of physics? I'd love to hear your thoughts in the comments below.